Welcome everybody to today's robotics seminar sponsored by Lockheed Martin. We have the distinct pleasure of having with us today Professor Gregory Chirikjian. He received his PhD from California Institute of Technology in 1992. He served in the faculty of the Department of Mechanical Engineering at Johns Hopkins University from sorry, I lost my bio for a second.
From 92 until recently, actually, almost
until 2021, right. Yeah. Quite a long time, right? And serving as a chair, indeed, from 2004 to 2007. So quite recently, he's made the transition to the National University of Singapore, where he now serves as the head of mechanical engineering department. Been busy, already hired 14 new professors. Dr. Chirikjian's research interests include robotic applications to group theory in a variety of engineering disciplines, applied mathematics, mechanics of biological macromolecules. He's been the recipient of several awards, including the NSF Young Investigator Award, Presidential Faculty Fellow, ASME Pi Tau Sigma Gold Medal. He's a fellow of ASME and IEEE. He's served as the program director for the U.S. National Robotics Initiative. He's the author of over 250 journals and conference papers and a primary author for 3 books. And I guess without further ado, I want to hand it over to Dr. Chirikjian.
Okay, thank you so much, Yancy, and it's a pleasure to be here with you today. I'm in Singapore, so for me it's 2 a.m. in the morning. But I'm feeling good nevertheless. I'll be talking about what I call robot imagination, and the subtitle is Affordance-Based Reasoning about Unknown Objects. So this is a relatively new topic for me in the last couple of years, and it sort of goes with my transition from JHU to NUS. So I've been out here for 3 years now, and there was an overlap period of the 2 appointments. Okay, so just as an outline, I'm going to wear my head of department hat at the beginning and give a brief introduction to Singapore and NUS, then talk about some older topics that I've worked on, and then get to the main topic. So this object affordances and what I call the spirit dictionary. So this is a map of Southeast Asia. Not everybody knows where Singapore is, but it's at the tip of Malaysia. Actually, I can't turn on my pointer, it looks like. So at the tip, bottom tip of this left green area is Singapore. Okay, so sometimes people say, Greg, what, you moved to China? Well, actually, no, Singapore is not attached to China, and it's several countries removed. So our NUS is it's kind of like the size of Maryland, of the University of Maryland, about 40,000 students, 25% postgraduate, and so this is my sort of my recruiting pitch. The startup offers are competitive. Faculty housing is right across the street, and it's a tropical climate sitting essentially on the equator, so you can swim outside all year long. And according to some rankings, the NUSME department is number 9 in the world, and the university 11 overall, and oftentimes listed as top in Asia. Okay, so this is what Singapore looks like. You have sort of on the left, sort of new greenish buildings, and on the right, you can see the contrast between the colonial architecture under British rule and sort of the new modern skyscrapers. And it's a very multi-ethnic, multi-religious society. You see various kinds of temples, mosques, churches, and it's possible to go for nature walks if you enjoy the tropics and natural beauty. Even though it's a major city, They retain the green areas and parks, and there's beaches and plenty of wildlife, monkeys and hornbills and other animals. As far as the NUSME department is concerned, we have about 1,800 students altogether. As I mentioned before, about 3/4 undergraduate. And the ME department has all the things that you'd expect in an ME department, you know, fluids, thermal, mechatronics and control, applied mechanics, etc. And we have a big manufacturing group. So Yancy mentioned the folks that I've hired. This is a picture of everybody who's joined since I've been the department head. And a few notable folks to mention on the upper left and lower left, Yu-Jun and Sun-Mi were recently 35 under 35 in the MIT Tech Review. On the upper right, we have Cecilia Lasky, famous for soft robotics and the octopus arm. And we've hired a bunch of people in 3D printing, materials, battery technologies, microfluidics, robotics, etc. So these are the folks that I'm proud to have hired over this time. Now going back to older work. So as Yancy mentioned, I did my PhD at Caltech, finishing in 1992 with Joel Burdick. And my topic was what we call hyper-redundant manipulators. So this is a bit of a tongue-in-cheek slide. I say hyper-redundancy, a concept whose time has come again. And I say that because these days continuum robotics is very popular. And essentially what's done in continuum robotics is to use a backbone curve and continuum modeling. And these are the sorts of things that I was doing way back in my thesis and the subsequent papers. So the idea of a hyper-redundant manipulator is that it has many, many degrees of freedom. And regardless of whether you have a variable geometry truss structure like the one here, or some other structure, we can do the planning and capture the essence and even do dynamics based on a continuum filament or backbone curve model. And so I've spent many years on this sort of thing with continuum filaments and modal decompositions to restrict the degrees of freedom. One example of which these days is piecewise constant curvature is a popular topic in continuum mechanics. But then I spent a number of years then taking these methodologies developed for hyper-redundant manipulators and applying them to DNA statistical mechanics. And I'll show that in a moment. But just to wrap up this discussion of hyper-redundancy, way back, 1990, we defined hyper-redundant manipulators to be those with a very large or even infinite number of degrees of freedom, as you would have in a continuum, and resembling snakes, elephant trunks, and tentacles. And the idea was that regardless of the specific details of the mechanical design of the manipulator, whether it's a serial chain with revolute joints or a rubberized tube or other kind of continuum or bellows or hybrid serial parallel manipulator, we could capture the essence of the shape with the backbone curve. And so that's where all of the continuum stuff really started. Another area that we've worked in is modular reconfigurable robots. And in particular, what I'm showing here is something developed by my former student, Matt Moses, which we call a universal constructor. And it's made of blocks which have cones on the top and conical holes in the bottom for easy assembly, and particularly easy assembly of a robot by a robot of the same kind. So we call this actually a self-replicating robot. And here's a video showing this in action. So the idea is if you have a stack of these blocks, this gantry-like robot can go pick and place, and put the parts together. You can actually see it's bolting them into place. So the end effector has a screw fixture which screws onto a part. Each part has screw threads on it. It screws on, picks it up, moves it over, unscrews, and bolts it down. So it's more than just Lego blocks. The structure is bolted together. And you can see that it's forming a second gantry. And so the first one is moving in one direction, and then the replica would move in the other direction. So, and so this led to some work on characterizing self-replicating robotic systems. We came up with a concept called the degree of self-replication. So if one is stacking 4 blocks, that is 1 degree of self-replication. If a robot is building a copy of itself out of hundreds of blocks, that's a higher degree of self-replication. And so why does anybody care, or why should anybody care about robotic systems that can build other robotic systems? Well, this concept actually goes back before my time. I was in high school at this time, in 1980. The Freitas report from NASA, Robert Freitas, was that on the lunar surface, one could develop a self-replicating factory that used in situ resources, therefore reducing the need to do launches and then build up capacity from a small factory. And at the core of such a small factory would be robots. And that report didn't have a lot of the technical detail about how the robots could replicate. So then we got into the act about 20 years ago and developed what we call an architecture for self-replicating lunar robots. And together with Matt, my former student, we wrote, actually all these guys are my former students, Yu Zhou, Jekrit Sudukorn. We had this more recent review on robotic self-replication. So not too different than self-replication is the area of team diagnosis and repair. So suppose you have a team or swarm of robots and one of them breaks down. How can the other robots diagnose that and repair the broken robot? So the idea is that each robot in the team is itself modular, and then each robot does a little dance every so often, and the other robots watch. And they formulate, in a Bayesian sense, a hypothesis about the state of the robot. So if the robot's dance is to do a figure 8, there's going to be some variation of what a normal figure 8 maneuver looks like. And then, and that's a statistical statement, probability distributions in the pose of the robot evolving in time, for example. And if that probability distribution has low variance around the figure 8 pattern, then it might be diagnosed as being healthy. If it varies widely, then characterizing the fault state is what this was all about. So this was the team diagnosis, and then the design of the robots so they're easily decomposable and repairable by other robots is the team repair part of this work. Behind a lot of what I've been doing over the last 20 years is a certain kind of mathematics, which electrical engineers should be even more comfortable with than mechanical engineers, in that the idea here is it's a generalization of Fourier analysis. So whether it's image or speech processing or whatnot, Fourier-based methods, FFT, convolution theorem are ubiquitous. And it turns out that the concept of convolution extends not only from translation of a mask, let's say, and doing template matching, but if you have a function on a group, such as the group of rigid body motions, or 2 functions, you can convolve them together. So there's a natural definition of convolution of functions on Lie groups, including SE3, the special Euclidean group of rigid body displacements that we often use in robotics. There's a concept of convolution, there's a concept of Fourier transform, which takes such convolutions and makes them into a product. In the Lie group setting, if you have a probability distribution, such as the case of the self-diagnosis work that I mentioned, you can define a mean and a covariance and look at how the mean propagates under convolution and how the covariance propagates under convolution. So I've used these tools quite extensively, not only in robotics, but in other fields. And well, I'll give you another example in robotics where these things show up. So the Kinematic Cart, the wheelchair-like robot with two independently steered wheels, if you tell it to go straight forward, in other words, you have the wheel velocities both be constant, you'd want it expected to go straight forward. But once you add on Gaussian white noise to each of the wheel velocities, which could be a model for jitter in the motors or slippage of the wheels, then the trajectories will splay out like in the picture shown here. And so we developed a model, a stochastic kinematic model for this kind of cart. And what results in terms of where the position of the cart is after some period of time, you get something called the banana distribution. So I didn't name that. That comes from the SLAM literature. And on the left here, you see the blue level curves of the banana distribution. And you can get that by doing many trials of a stochastic differential equation, or there's a corresponding partial differential equation, a Fokker-Planck equation, which directly propagates the probability density. And so you look at that banana distribution and you say, obviously it's not Gaussian because the level curves are not ellipses, but that is in XY theta coordinates. But if instead we use exponential coordinates for this Lie group, the group of rigid body motions of the plane, which describes the position and orientation of the robot, then we showed actually that this banana distribution is Gaussian, but in those exponential coordinates. And so that comes back to the list of mathematical equations that I showed earlier. And the same mathematics applies elsewhere. I mentioned DNA modeling before. We actually publish in the physical chemistry, biophysics literature. So if instead of time being the independent variable of where the kinematic cart goes, if you have DNA subjected to Brownian motion and you capture the shape of the filaments, then and if you anchor, let's say, the base, you get the same displaying of configurations. Here, it's not, trial runs of stochastic differential equations evolving in time, but rather it's sort of you can think of it as like a bouquet of configurations of DNA. And so it's actually, it's exactly the same equations as the kinematic cart. For DNA, it's in 3D though, as it is for kinematic needle steering, which is another area that I've worked in. But actually in this particular paper, things were 2D because the DNA got adsorbed onto a surface, and our experimental collaborator, Martin Goodhold, used an AFM to trace out the DNA shape. And the application here was to determine where along the DNA filament a cisplatin, a chemotherapeutic drug, was binding, because it was the binding of that drug and the bending which inhibits the replication of the DNA, particularly in testicular cancer is where this is used. And the bend is so subtle that you can't tell just by looking at one instance of the DNA molecule that's cisplatinated. But by looking at the ensemble behavior of the end-to-end distribution of the DNA length, one can determine where the cisplatin bound and, in fact, what angle it induced on average. So we solved mathematical inverse problem in DNA statistical mechanics using the same tools as what we've been doing in robotics for many years. And so once you work in a number of different areas, you can publish in IEEE, you can publish in Biophysical Society, et cetera, and a few people in each place know what you're doing, but tying it all together in books is something that I've been doing quite a lot. So, anyway, the harmonic analysis is about not only classical Fourier analysis, but also Fourier analysis on Lie groups. And then this other two-book set is about the union of stochastic modeling, such as stochastic differential equations, Lie groups, and I've just shown you an example of a stochastic model evolving on a Lie group with the kinematic cart, as well as information theory. So once you have convolution theorems, sampling theorems, et cetera, and you go to the Lie group setting, that's a connection between Lie groups and information theory. So these are the sorts of connections that I've made in the past. Okay, so now that's after all of that long-winded review of older things, I want to get to the brand new topic, which is object affordances, which I'm very excited about. And this is a topic that I started thinking about really while I was at NSF. And I'll tell you about this concept of the Spirit Dictionary. Okay, so my old papers all have titles like, convolution theorem, harmonic analysis on special Euclidean group, operational properties, and, very mathematical. My new papers are all relatively simple titles and from the perspective of the robot. So one was in 2020 at ICRA. Our first paper on this topic was called, this is the title of the paper, Is That a Chair? And then ICRA 2022, we have a paper, Put the Bear on the Chair. And we're working on a paper called Prepare the Chair for the Bear, which involves turning an upside down chair upright so it can be used. And then at IROS 2021, this last one, we had a paper, Can I Pour Into It? And the I here is the robot. And that was a finalist for best paper in the human-robot interaction area for IROS 2021. So I'm going to actually show videos from all of these works coming up. But what is meant here by robot imagination is that unlike learning, where you're presented with many instances, whether it's Mechanical Turk annotated images fed into a deep learning algorithm, or whether it's imitation learning or other kinds of reinforcement learning, where there's many instances and of something being observed. What I call robot imagination is when the robot has not observed anything, okay, and it has not been trained. There's no prior big data set, and the robot is presented with a new object, and it needs to figure out what kind of object that is and how can it be used. That's the essence of affordance-based reasoning. And well, at Maryland, you have an expert in this, Yanis Elamoidis, and well, multiple experts, but and so I think that this topic should resonate with a number of people in the audience. So let me get to it. So if you look, what is the current state of the art of robots in the service environment? Well, you have things like, robots cleaning floors, and this is a robot greeting people at the lobby of this hotel. This happened to be a hotel in China before the pandemic, but they're not very smart. I just waited to watch this happen. Obviously, they have no grounding, no sense of proprioception of self or whatever. And so they just sort of bang into each other. And so what we want to do is endow robots with a higher level of intelligence. And so, and the application is elder care, especially in East Asia, whether it's Japan, Korea, Singapore, China. The aging population means that this sort of Jetsons style robot may become popular in the future. But if you're going to have robots interacting with people, they need to have much higher level of intelligence than what they have now. So of course, there's related work on object affordances, affordance-based reasoning, and this is, this is an incomplete list. It goes back to J.J. Gibson, a psychologist, in the way humans perceive objects and how they're used. Rujna Baichi, when she was at UPenn, and she's back at UPenn now as an emerita professor, worked on, of course, active perception, as well as Yanis and other people. But the affordance side, as I mentioned, folks at Maryland have been working on affordances, and folks in Europe, but not there's not a lot out there, I would say, in the US, more broadly speaking. I mean, but I think it's picking up. And so this is this is basically my direction going forward. I'm continuing with the more mathematical work, but this is one of my main topics now: object affordances and what we call the SPIRIT dictionary. So SPIRIT is a forced acronym. It means it's spatial information rich interaction-based task dictionary. So the idea is that if you're going to have robots that can adapt in a home setting, they need to be able to handle, to deal with objects that they haven't seen before, but the object classes are known, such as cup or chair or table, okay? And the object is not defined by how it appears, but it's defined by how it is used. That's the essence of affordance-based reasoning. So in my view, this SPIRIT dictionary fits at the center to link several areas in robotics together, whether it's active perception or knowledge representation, natural language processing. And this is sort of, from my time at NSF, I noticed there were a lot of proposals very targeted in one area or another area, but something was kind of missing in the thinking in the community that could tie together multiple things. So my argument is that this SPIRIT dictionary can tie together many things. So it's a bit abstract about what do I mean by SPIRIT dictionary, but I hope it to become clear when I show examples. And so I'll just say the dictionary consists of common items that you would find, let's say, in the home, such as a cup or chair, and the objects are defined by how the robot would interact with the objects and use them, okay? And so when presented with a new object that it doesn't have a database of anything except the definitions. So in a sense, this is like the knowledge base for an expert system. You might call this knowledge engineering, which is not popular these days given deep learning, et cetera. But I hope to show you here and demonstrate the capabilities of this way of thinking as compared to the current thinking in the community with regard to learning. So essentially, what is a chair? A chair is something that affords the object of sitting. A cup affords containment of liquid. And so if robots are used in unstructured environments, relatively unstructured, I'm focusing on the home environment, the hospital environment, where there may be previously unseen objects, and how can the robot identify the affordances? So here's the first foray into that. So is that a chair? So this was this ICRA 2020 paper. So there are many different kinds of chairs. They have many different appearances. And you know, you can also have a dollhouse chair that looks like a chair, but you can't sit on it. Or you could have something that looks like a chair, but is missing a seat, so you can't sit on it. Or you might have a picture of a chair on a wall or whatnot. And so based on appearances only, we can't say an object is this or that. You could have the teacup ride at the amusement park, which you can actually sit in the teacup, so it is a chair, even though it looks like a cup, right? But you can't use that as a cup because it's too big. You know, so appearance-based things have their limitations. So the idea of, is that a chair, is the robot comes to an environment, say that the robot, you take it out of the box, it's a new robot that's just brought home. There's a chair, it doesn't know it's a chair, and it's turned on the side. How can it reason whether it's a chair or not? Well, first of all, this chair at this orientation does not afford the sitting function. But if the chair is rotated, then it will afford the sitting function. So the idea is that the robot will go, it will scan the environment, it will classify whether the chair is sittable, and then determine what orientation it needs to be at in order to afford that function. So here's how the pipeline works. So there's arbitrary objects at arbitrary orientation. The robot scans them, puts them into what we call the imagination framework, which is physics-based simulation of the scanned object, which is put into the physical simulation. We drop the robot imagines dropping the object from many different orientations to find where it can land stably. And then we have a humanoid figure and we drop it on the objects at their various orientations and determine whether the humanoid figure can stably sit. And then, you know, from this we find not only, yes, this is a chair, but actually this is the orientation that the chair needs to be at in order to be used as a chair. Okay, so so here are some some more results along those lines. We did this with synthetic chairs in simulation, as well as real chairs that were scanned and then put into the simulation. And by the way, another area of our work is taking 3D point clouds and parsing them out and developing unions of superquadric models to capture the essence of the point clouds with relatively few parameters. And we have an CVPR, sorry, it's 2 o'clock in the morning. We have a CVPR paper on that in the upcoming CVPR on how to capture the essence of point clouds with unions of superquadrics. So here's really this is the most telling slide, I think, with regard to the chair. So you have the chair model. It's been dropped at different orientations. The stable ones have been found. And then we drop the passive humanoid figure. And then we find that the upright chair, as we would know, is the way to use the chair. So then the next step, and this is a ICRA 2022 paper coming up in May, is how to use that information to have the robot do something. So here we see this Franca robot on the left is doing the scan of the chair. Then we put the scan into this imagination framework. We find this is the best way to sit. And then the now's job is to place a teddy bear on the chair. That's put the bear on the chair, okay? And so, so the chair at this orientation, the now is saying it cannot reach it, and it asks the human to rotate the chair. And because we do quite a lot of motion planning in my group, we've developed a motion planning framework, which we're using in this context. And I mean, it doesn't look like a very impressive thing for the now to walk straight forward, but it includes an articulated model of the teddy bear. It includes the robot imagination of the chair. This is a previously unseen chair, not modeled. There's no knowledge of the shape of the chair in advance. And it's all done, it's not real time, it's relatively slow, but it's all done, you could say, on the fly without prior knowledge, okay? And so this was one aspect. Yeah, so, and it works with multiple different kinds of chairs, okay? Now, so we've done, you know, I don't, maybe 50 different chairs, and it works consistently. And we've done it with things that are actually not chairs, but afford the sitting functionality. Like in the lower right here, it's not really a chair, it's really a step ladder. And we've done it with other things also, like they'll be coming up an example where we constructed a chair out of copies of my books, which you know, deep learning might characterize as a bookshelf or something, but this recognizes the affordance of sitting for the bear. Now there's an aspect of the human robot interaction in this, which is that the human is being asked to reorient the chair so that it can be reached. And so then we said, well, what if the human is naughty and rotates it the wrong way? And so, you know, so the human rotates it. On the lower left, you can see the makeshift chair, which it recognizes as affording sitting. So the robot recognizes, okay, I can't reach there. You didn't follow my instructions. Please turn it the other way. In the case when the human doesn't obey the initial instructions. Okay, let's move on here. Oops, this is repeating. Okay, so the next work is what we call prepare the chair for the bear. And that's when the chair initially is not upright in its functional pose. So here, again, it's the same methodology. We do a scan with a 3D camera. This chair has handles attached so that the parallel jaw gripper can reorient it. We're not focusing on manipulation here, multi-fingered hands. So we're taking that problem out by putting these handles on things that we want to manipulate. It's scanned, and then it's scanning the top here, and then it puts it in the imagination framework, the simulation environment, and then just like before, to know how can it, what is the orientation to be used as a chair, and how can the robot reach it. So it puts it at the right orientation for the now to deliver the teddy bear. And so this was prepare the chair for the bear. Of course, you know, the now is just taking a few steps forward and putting it down. We have the capability for the now to go through an obstacle field and put the teddy bear on the chair, but that, I mean, that's not the main point that we want to make. The point is the sort of the pipeline and the architecture for imagination. Okay, so and then related to this is the work that I mentioned that we presented at IROS 2021. My student Hongtao Wu has been leading many of these efforts. And this is, can I pour into it? Okay. And so basically this is to determine, is something an open container, such as a cup? And so here's a teaser of how this works. So all of these objects there's a plexiglass stand there. All of these objects are previously unseen. Okay. And they were scanned, and then the robot assesses them as something that you can pour into. Okay, the container which initially contains the M&Ms is known in advance, but what is not known is the container that's receiving the M&Ms. So there's a lot of work out there that's been done on simulation of liquids and pouring, but usually it's for previously known objects. There are deep learning based things like Affordance-Net, where there's many instances of previous containers and other objects that have been, annotated and whatnot. But here we're focusing on a priori unseen objects. So the idea is, can the robot imagine open containability using a framework similar to what I showed for the chair? And so the essence of an open container is, can you pour something into it and retain what you've poured rather than having it, spill out? And so so here is an example, a couple of examples. The robot scans again, puts the scan in the physics-based simulation. And here we drop a sheet of beads and ask, how do beads get retained in the object? And if it's a roll of tape with a hole in the bottom, then the beads will pass through. So it might look like a cup, but it doesn't afford containability. And then the object up here, it's a paper cup of some kind, does afford containability. So, so that's how the framework works. And this, it consistently works as well. This sort of half coconut looking thing is scanned. It had never been seen before. Then in imagination, it is shown to afford, containability. And so then the robot then goes and pours into it. So here's the imagination. We get a footprint of the beads that get retained inside the object from that, and then we sort of, accelerate and tilt the object a little bit to see if it stably is containing the beads. And then from the footprint, we get information about not only how many beads go in, but where should we pour. So we choose the center of mass of the footprint to be the place where we pour. And then there's simulations of what angle of pouring and which direction to pour from. So it's all simulated to give foresight of action before the robot commits in the real world. So that's why, that's imagination, right? You think, you imagine what might happen if you do this or that before taking action. So imagination, foresight, these are things that we're very interested in. And so then after it's done this scanning and imagination, the robot just goes and it pours the beads into the real container. And we've demonstrated this on 100 different containers, and it works very, very consistently, some 98% of the time. Now, that doesn't mean it works every time, and I'll show an example, but we did a comparison with many different objects, both container and non-container, and it could very well categorize whether the object was a container or not. And you can look at numbers of how well it's done. So let me go back here. Okay, so, oops, sorry. Okay, so so here you see the beads dropping down on different things and seeing which can contain and which cannot. And it works very, very consistently in terms of categorization. And then after categorizing, then there's the actual pouring. And that also works very, very well. We've done many, many examples, as I said, 98% success. One case where it didn't work is coming up. Okay, so well, actually, I guess in all of these cases it works. So even this candlestick holder, which is, you know, would a human call that a container or not? But the moat around the side affords the beads more than the hole in the middle. Okay, so it got that from the simulation. But here's one example where it failed, where the neck of this vase was too narrow. So it characterized it as an open container, but when it went to actually do the pouring, it failed. Okay, so well, 98% is not too bad. And so this is, you know, I basically have shown in this talk two examples, the chair example and the open container example. But we're developing this dictionary to have initially 25 different object categories in the home, and we're open sourcing it, and we want to build this spirit dictionary out so that robots, you know, worldwide can reason about previously unseen objects, and not only reason about them, but then go and manipulate them in the real world using this combination of sensing, active vision, as well as robot imagination, physics-based simulation of affordances of object categories, rather than specific instances of objects or you know, big data-based approaches. Which is not to say that things can't be blended. I mean, there are certainly cases where using learning makes a lot of sense, and it might even be that learning is trained on the physics-based simulation rather than simulating everything every time. But this is just to demonstrate the framework of how simulation can be used in the context of previously unseen objects. So I'll stop talking with that, and you know, these are what I talked about. You've just seen it, and I'm happy to take any questions at this point.
Well, thank you so very much for that presentation. I think the bears were adorable. I'm gonna go home and show this to my daughter. She's gonna get a kick out of it. The one thing that she might like more than bears is robots. So.
Well, we need to do robot bears.
That's right. Do we have any questions from the audience? Let me go to the Q&A. We have one from Derek Bailey. Can you describe the trade-off between confidence and speed in the imaginary scenarios considered prior to taking action, especially in the light of computation limits?
So this is very computationally intensive and currently not real time, but we can imagine a time in the future where multiple cores are running simulations in parallel on the fly, or we push these simulations to the cloud and get an answer back. So I'm not too concerned about the time issue. It's more to get the framework out. But of course, there is always a trade-off in time and confidence. I mean, the more simulations you do, the more confidence you will have. But we haven't really looked at that trade-off in any detail yet, because we're sort of pushing that to the future, and maybe we're being rosy and optimistic that the computations will be parallelizable or be able to be handled in a way to make this a real-time thing. And even if it's not real-time, you know, if you have, you know, grandma is living alone with a new robot, maybe while she's sleeping, the robot can roam around the room, scan things, do the simulations, dream at night, do the imagination at night, and then the next morning it's ready to go. So there are ways to get around the time issue, but it is an issue that it's very intensive computationally and time-wise.
Great, thank you. And I should mention, if anybody wants to ask the questions themselves, use the raise hand feature and I can allow you to speak. I have a question from Dinesh Manosha, more or less in line with the one that I had myself. So the question is, how much accuracy do you need in terms of the physical-based simulation? How does it impact overall performance? And a follow-up question, I suppose, a key issue in simulation accuracy are the material properties.
Yes, so the material properties are that's very interesting, because you can have something that looks like a cup, but it's made out of paper, and so then if you try to pour into it, it might melt or something like that. But we humans also, if we look at things, can be mirages and optical illusions, and so nothing will be perfect. But I guess the idea of the imagination is it's scanning by vision first. There's nothing that limits us from tapping on things and getting data through manipulation as well. That can also be built into the model. So far, we've just been using the 3D point cloud scans because that reduces our need to do manipulation. But it certainly can, material properties are important and can be worked into physics-based simulations as well. I'm not sure, Dinesh, if I completely answered your question, and I see your hand up. Maybe you want to just ask it directly?
Yeah, okay. Thank you, Greg. First of all, thank you for giving a talk at 2 a.m., but I guess you anyway don't sleep, so that's okay. So this is, one question. So there are two ways to physical simulation. One is the classical engineering simulation, how much accuracy you need. And recently, people are solving the same problem that you solved about. There's a lot of work on using learning, reinforcement learning. And there's a big push towards what we call sim to real. You train in simulation and try in the real world. I myself tried some ideas there. And folks have a different opinion of how much simulation fidelity you need. So this simulation accuracy is a classic problem in engineering simulation, robotic simulation. And now with the learning framework, people are asking this question. So I would just get to hear, what kind of experiences you have. You talk about time, running time, we can handle it. Things will get faster on cloud. But how much simulation fidelity we need? That's a big question right now.
Yeah, and we're using PyBullet, and there are other things that are maybe better, and NVIDIA has its own framework. So the fidelity of the simulation is an important aspect. But I think robots have an advantage in that we can program in Newtonian mechanics in our own human imagination. We don't necessarily, we don't have Newtonian mechanics built in, right? We have experience, and we have sort of a vague picture of the future and act on it. So yeah, I think that there's a lot of opportunity, and yes, the sim to real, real to sim, and in the learning community is a topic, and this imagination idea is something that can fit in as a module within a learning framework, or it can stand on its own, I think. I saw Nikhil Chopra had a question, but Nikhil, do you want to just ask it?
Yeah. Hi, Greg. Nice talk. Thanks. Good to see you again. Long time. Yeah. So just wanted to kind of ask, you mentioned in the earlier part of your earlier work, one of the first things that when you're doing your PhD and after that as well, on hyper-redundant manipulators. So you mentioned the PCC assumption that people are using, including us. We have been adopting that for developing some dynamics and control algorithms for some dexterous soft robots. So I was just wanting to understand what is the similarity between your earlier work, your modeling framework, and the PCC assumption essentially.
So the hyper-redundant work, and all of that led me to the more mathematical side with probability distributions on Lie groups and convolution and Fourier and all of that. In the present work, when we do simulations and we do an ensemble of simulations, and there's variability, and there's the point cloud scans will have some error associated with them. The connection there is really through the mathematics. There's nothing snake-like in what we're we're doing with the affordance-based reasoning, but the sort of the trace of the mathematics that resulted from the snake work has applicability in characterizing error propagation and uncertainty and things like that. So that's what I would say. It's like one step or several steps removed from the hyper-redundant work, but the the path that led us here is connected.
I see. Thanks.
Thank you, everybody. Any other last questions? I want to take a moment to thank you again, Greg. This is a great talk. I really enjoyed it, and I'm sure a lot of the people in the audience did as well.
Okay.